In the same way that we talked about properties for expectation, we can also define some properties for variance. Now, the conceptual definition of variance is given by this expression, but what's going to be a little bit more useful for us is that if we write it in a different way. And what I mean by that is mu is just a placeholder symbol for the expectation of x. So a little bit more clunky is this, but we actually like this version a lot because it represents an expression or a definition for variance in terms of function notation. So that means whatever variable or whatever expression is placed here, it gets placed there and right there in our formula. And just like we did earlier, if by chance you ever need to take some function of that random variable, then the expectation formula gets adjusted in a very straightforward way. Just like we did above in blue, everything that you would see, wherever there's an x, it's going to get replaced with a g of x. So it does get a little bit clunky with all the brackets, but this is the useful property for expectation, for variance. And one of the most important uses of it is, again, a variable that is essentially a linear function of another one. So it's some linear function of the original. And according to what I just wrote above, this would be ax plus b minus the expectation of ax plus b. All of that business would get squared. Now it's starting to get messy and a little bit overwhelming perhaps, but to try to simplify it, from the previous video, this is a mu plus b. So on the inside here, we're going to have ax plus b subtract a mu plus b. That expression will be squared. So that kind of conveniently gets rid of these shifts, and then we'll get ax minus mu. And with the squaring property, that ends up giving us this particular expression. Now, by definition, if you wanted to think of it as the definition with the sigma notation, we'd get an a squared xi minus mu squared pi. So we could just take that outside, and this would end up giving us an a squared times the sum xi minus mu squared pi. And the point of the story here is that this is the variance of x. And so we end up with a really important result. Sorry about all this zooming. If you were ever to take a random variable and do a shift and a stretch, right? Remember from basic pre-calculus that if you were to shift and stretch your variable, all that's going to end up being the case is that you will just get the shift ignored and the stretch will be there. So if you were to take a random variable, and if it were to have some sort of mass function, if you were to shift it and stretch it, so if you slide the thing over and then make it taller or shorter, all that this formula says is it only cares about the stretch, not the shift. And that kind of makes sense, right? If you slide a variable or a graph left and right, you haven't changed its spread. All you've done is just changed its location. So its variance shouldn't change. But soon as you start stretching it, then you've changed the relative position of all the outcomes relative to the mean. So that does say that you would get some difference in terms of the variance. Now, that's a mathematical property, and that's great and all, but what we need is some intuition here. So as this final note, what can we do with variance and standard deviation? Now, standard deviation ultimately ends up used more. Sorry about that. Ends up getting used more because it has the same units as our variable. So one of the really important things that we do is and use standard deviation for is something called relative score. So for instance, we could create a new random variable where we take our old one and we subtract from it the mean and divide it by the standard deviation. And the question here that we ask is, how many sigma jumps is x, let's say xi, away from mu? And this is what's called a relative score. When I give you an outcome or a value of the random variable, I want to know how far away it is from the mean, not in an absolute sense, but in terms of jumps of sigma. And that's why there's a sigma on the bottom. It's going to turn out that in the theory of probability, relative jumps like this, or jumps in terms of standard deviation, become important. And here's an example of that type of thing. So this is something called Chebyshev's inequality. Now, Chebyshev's inequality, I've written the statement out on the formula, on the sheet attached here, the PDF. But basically it says, look, if I've got a random variable and it's got a mean of mu and a variance or a standard deviation of sigma, it's, as the title says, an inequality. Now I'm going to write it out here. But basically it's talking about standard deviation jumps. And the statement of the formula is not particularly enlightening, but if you're to look at a picture, so let's say we had our random variable having a mass function that kind of looked like this, and let's say that the mean is somewhere here. Chebyshev's inequality is a statement about how much of this distribution or this picture you can gather up by giving it a big hug. And you say, a hug? What the hell do you mean by that, right? Okay, so C is a number that has to be greater than 1. So if that's the mu there, I can essentially stretch my arms out and say, let's say that's a spread of sigma. Let's say that distance right there is sigma. So this would be mu plus sigma, and this would be mu minus sigma. If I were to go another jump of sigma, I'd get to mu plus 2 sigma, and I'd get to mu minus 2 sigma. And then I essentially wrap my hands around the distribution, and then I say, okay, give it a hug. And how much of the outcomes, or how many, what proportion, how many of the outcomes fall within plus or minus 2 sigma of the mean? Well, Chebyshev's theorem, or inequality here, tells us that. So when C is equal to 2, the proportion is going to be 1 minus 1 over 2 squared, so 3/4. And that means at least 75% of the outcomes live within 2 standard deviations of the mean. So this is kind of a powerful result. Now, if I were to go one more standard deviation, mu plus 3 sigma and mu minus 3 sigma, you can see from this picture that most, if not everything, is contained within those green bars. And so if c is equal to 3, it would be 1 minus 1 over 3 squared, which is 8/9. And it would say at least 89%, at least, could be more, of all the outcomes are within 3 sigma of the mean. So this is an incredibly powerful and general result. It says it doesn't matter what random variable you have, as long as it makes a mass function that follows all the mass function rules. If I stand at the mean and stretch my arms out 2 standard deviations and hug the mass function, I will hug at least 75% of it. Maybe more. I might even hug all of it. If I were to stand 3 standard deviations away from the mean, stand at the mean, stick my arms out 3 standard deviations and give it a hug, I would be hugging at least 8/9, maybe the whole thing. And so what you should take out of this is that Chebyshev's inequality says that almost all of the outcomes live within 3 standard deviations of the mean. And this is a theme that we're going to go on and make precise for specific mass functions as we go throughout this the next chapter. The standard deviation is this built-in measure of distance that says, look, if you are about 3 standard deviations from the mean, you're pretty much going to have every one of your outcomes there. So I've attached a proof of Chebyshev's inequality, a mathematical proof, but what's important is that you understand the idea intuitively and be able to work with it with some basic examples at the beginning.